So in the previous session, we were discussing that we have proved two results. One is probability of phi is equal to 0. And another one is, number 2 is probability of the event A happens, or probability of event A and probability of event A not happening together implies 1. Very fundamental result. Here I am posing one question which you must think of. The question is that we know that for any impossible event, probability is 0. We have already proved it. If we have an event A whose probability is 0, does it imply always that A is impossible? This is the question. Very important question. That means whether this particular result that I have proved, whether it is unidirectional result or bidirectional result, is it both way true or it is only one way true? Probably you are thinking that yes, of course, it is both way true. The answer to this question is no. There may be events which are having probability 0, but these events are not impossible. This will be explained in module 2 of your syllabus. So you have to wait patiently to get the answer to the given question. But it is an interesting question, and you just put a star over here. Now, let us come to this particular part. Probability of the happening of the event A and probability of not happening of the event A is equal to 1. This happens only when I'm considering capital S is the sample space and capital A is the event inside it, and capital A bar is the event, so that A and A bar together define the entire sample space. Other than A, inside this sample space, no other events are there. With this approach, with this basic notion, I have proved this particular result. So do not remember the result only, remember the figure also. Whenever you study something, study it carefully. Number 3 property was, so far as I can remember, that B is the sub-event of capital A. Diagrammatically, you know that I'm not actually writing here, I'm not drawing here the sample space because it is present over there, we know. I'm only drawing the inside event, that is capital A, and I'm drawing capital B because I'm interested in capital A and capital B. B is the sub-event of capital A. Now, we want to show that probability of the sub-event is lesser than or equal to probability of the bigger one. You see this Venn diagram, from this Venn diagram, that capital A, this big event, can be expressed with the union of two mutually exclusive sets. I can write capital A as B union A intersection B bar. What do you mean by A intersection B bar? What do you mean by A intersection B? From set theoretic approach, it means an element present in both A and B. This is the set theoretic approach. From probabilities perspective, it means capital A and capital B are happening simultaneously. All the outcomes that define capital A are similar to all the outcomes that define capital B. Okay, so if we have A intersection B bar, this implies A is happening, but B is not happening. And this is in simultaneous way, it is actually, we are getting this particular situation. At one point, one event is happening and simultaneously the other event is not happening. This is what we actually define by this expression A intersection B bar. Similarly, if I write A bar intersection B, it implies that at one point A is not happening and simultaneously B is not happening. B is happening. So we have this situation. So if you look at the Venn diagram, you will see that A intersection B bar contains outcomes in this region. Here A is happening where I have put the dots, but B is not happening. So I can express this, I can consider this portion as one set, which I have written over here, and the inside is B, which is another set. And from the figure, it is pretty much clear that they are mutually exclusive. And so that I can combine them with the notation of union, and that defines the entire event capital A. Now I am applying probability on both sides. Probability of A is equal to probability of this thing, probability of B union A intersection B bar. Okay. And this is equal to, this implies probability of A can be written as probability of B plus probability of A intersection B bar. Why? Because from axiom 3, once again, we know that since they are mutually exclusive, I can add their individual probabilities. And we can express probability of A intersection B bar as probability of A minus probability of B. But a few minutes ago, we have proved that, or not proved, in the axiom, we have assumed that probability of any event is non-negative. By axiom 1, we can say that we know that A intersection B bar is any event. And by axiom 1, we can say that the probability of it will be non-negative. If it is so, this will imply probability of A minus probability of B greater than or equal to 0. This implies probability of B less than or equal to probability of A. So thus we have proved that if B is a sub-event of A, probability of the sub-event is less than probability of the bigger one. You quickly take the screenshot of this page. I'm moving on to the next page. Okay. If you are not able to write it, then just quickly take the screenshot. And I'm going to move on to the next page. Okay. So far we have proved 3 results. And if you carefully observe that in each of these 3 results, I have applied the axioms. I have never deviated from the axioms. Now let's get into the next result. Okay. Number 4, I was supposed to prove that probability of A is lying between 0 and 1. We all know this. Okay, but we do not know how to prove this particular result. This particular result has 2 parts. One part is that we need to show that probability of A is greater than or equal to 0, or we need to show that probability of A is less than or equal to 1. First part, this is my first part. This is my second part. If I can show both the parts are happening, that will prove, we can say that, yeah, this result is valid. First part is pretty obvious. We don't have to prove anything. Probability of A is indeed greater than or equal to 0. And why it is so? Because of the axiom 1. And I told you that axiom 1 cannot be proved. They can only be tested. Let's talk about the second part of the problem. For the second part, we know that when we talk about any event capital A, this event is a sub-event of the sample space capital S. Okay, because if capital S is the sample space, A is a part of it. And just now we proved in the previous page that if B is a sub-event of capital A, then probability of B is less than or equal to probability of A. So by applying theorem 3, we can say that probability of A is less than or equal to probability of S. This implies probability of A less than or equal to 1. Why? Because of axiom 2. So from both first and second part, we immediately see that this result is valid. Now, keep in mind that some authors, they replace the first axiom, which is probability of A greater than or equal to 0. Instead of writing this, they take probability of A less than or equal to 1 to be the axiom. So if you consider this part to be the axiom, you can prove this part. If you take this part to be the axiom, you can prove this part. So there is a kind of cross connection between these two. You cannot prove them simultaneously. You can consider this to be the axiom also. Then your probability of A greater than or equal to 0 becomes a theorem. But since we have considered probability of A greater than or equal to 0 to be the axiom, this becomes our theorem. Very interesting. I shall talk about this particular part, this particular theorem once again. But before that, I'm going to give you a hint for the fifth theorem, which we have with us as probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. I'm not going to prove this particular result here. You try to do it by yourself, but as a hint, I can say that you consider two sets. They are not mutually exclusive, because if they are mutually exclusive, they will be mentioned in the question. So we have A, B, and you know that this part is A intersection B. And this part, this left-hand side part is the event that A is happening, but B is not happening. This right-hand portion is the event that A is not happening, but B is happening. Now, this is hint number 1. This is hint number 1. Hint number 2 is that try to express A union B as a union of these three mutually exclusive events. I'm writing it for you. Now you apply probability on both sides and try to find out the result. You don't have to do it right now. Do it after class and whenever you find your leisure time of doing mathematics. So this result is very important, and it is pretty much similar to the result which you know from your school days and which is connected to set theory. The two results are pretty similar, looks very similar. Here n of A union B, NA plus NB minus n of A intersection B, where n represents the cardinality of the set. But don't apply this approach. Do not apply the approach by which using the cardinality of the set and the classical definition of probability and considering the events to be equally probable, we can prove this result also. But I'm not saying the events are equally probable. I'm saying that there are any events. I do not know whether they are equally probable or not. So do not apply this result. Apply it from axiomatic point of view. Now, let us come back to this particular part. Question number, property number 4. We have proved that probability is a kind of thing which is lying between 0 and 1. What is so interesting about it? It's very pretty interesting, but you do not know. I'm going to talk about this in the class. Something has to be different in the undergraduate course, isn't it? In the graduation course, something has to be different. So why it is so important? It's going to talk about, it's going to tell us, give us a solution to my earlier post question. What is the probability? What is the probability of getting head by tossing a biased coin where randomness is present? So now I can reply to this question, I can reply to the given question with the help of this. How? Since the coin is biased, so head and tail are not equally probable. So I am assuming the probability of head is equal to small p, and probability of tail is equal to small q. Or we can write 1 minus small p, because why can I write this? Because we know that probability of t and probability of t bar, if I add them, this gives us 1. Probability of A plus probability of A bar equal to 1 from our theorem 2. Probability of T bar is actually equal to probability of H. Tail is not happening. So what is happening? Head is happening. So we can consider this to be in the following manner that I have written. So we have these two probabilities. Only important part is this. So if we know P, we know Q, because P defines Q. Only thing that you have to keep in mind that this number small p lies between 0 and 1. So keeping this in mind, if I ask a person about this particular question, he can immediately reply that, yeah, for a biased coin, the probability is 1/3 and probability of tail is 2/3. This answer is correct because it is satisfying this rule. Another person can reply that probability of head is 99/100 and probability of tail is 1/100. By keeping this rule in mind, you can actually talk about various probabilities for a biased coin. Various probabilities can be talked about. There is no limit in this. Infinitely many answers to the given question. It's very interesting part. And another interesting feature of this particular thing is that I'm going on to the next page. Please take the screenshot of this page. Another interesting feature which comes from this problem number 4 is the following. I'm moving on to the next page. Take this. I hope that you have taken the screenshot. First of all, I earlier said that A is event, and which means subset of sample space. So whenever we write probability of H, this is similar to the case when we write probability of the set which contains H. But since it takes lots of time, so we actually omit the braces in which H is the outcome. H is not the event, it is the outcome. But if we contain this outcome inside a set, then it becomes an event. So this is my event A. But for simplicity, we just omit the braces and we write H. So you just keep this in mind. It's very important. This part is very important. Nobody has ever told you before that. Second important part is that we thought so far that we toss a coin, we spin the coin rotates, and somehow mathematically we can calculate the probability by using the classical definition, favorable number of case by total number of case. Important point that I need to say here at this point is that probability cannot be calculated. Very much, I think this particular statement, probably you are actually not very much familiar with this. Probably you are hearing this particular statement for the first time. Probability cannot be calculated. There is no way by which you can get the favorable number of case by total number of case. This is just a notion that we have. It's kind of symplectic approach. Like considering the coin to be unbiased, we thought that yeah, classical definition can be applied, but this is not the case. What happens is that in probability theory, we have the sample space capital S, and suppose we have a event capital A, and suppose we have an event capital B. What we do is that, if you carefully observe, we impose, when we write, we try to find the probability of event A and probability of event B. They may be mutually exclusive, they may not be mutually exclusive, whatever it is, we try to impose some values on the probability or on the event. We try to impose some number on the event forcefully. So probability is a kind of function also. It is a kind of function. Okay, what sort of function? Probability is a function whose domain is the maybe the sample space, or whose domain may be the sub events of the sample space, but whose outcome is the set of real numbers, which is actually the closed interval 0 and 1. So probability is a function. We impose the values, we do not calculate the values. Just look at the previous problem. The person, after knowing this result, is putting, according to his will, several values to the respective events. He is putting 1/3, 2/3, 99 by 100, 1 by 100. He is putting 1/4, 1 by 4, 3 by 4, and so on. There is no limitation. Is he calculating? No, he is not calculating. He is imposing. He is imposing the values on it, on the event. So probability cannot be calculated. This is another important notion that is pretty much important, and you have to keep this in mind. That we do not calculate probability, we set the values according to our wish and we impose it on the event. If you ask a layman about the game of chance, what is the probability that when head occurs, tail also occurs, then the layman will say that yeah, 50% chance is there, half of chance is there. He doesn't know about the probability, but somehow he can guess it. What is the mystery of that? The mystery of this lies in the fact that he somewhere in his mind, without actually realizing, he is assuming that the events, he doesn't know about the word event. He assumes that the things of getting head and tail, they are equally probable. So he is he do not know about the classical definition of probability, but very smartly he can answer to the given question. Very smartly he can answer to the given question. Why? Because he is not at all calculating. He is just imposing the values. But when you say that, okay, I am giving you a broken coin, now you tell me what is the probability of, then also, if he is a little bit of intelligent, he may reply to the question or he may not reply to the question. He may reply that, yeah, then also it is half and half. But if he is little bit intelligent, then he will say that, broken. It's a broken coin. You just don't use it. You give me a fresh coin, then I can take. Okay. So remember, we do not calculate probability, but we just impose values. Now look at in your WhatsApp group. I have actually sent you a screenshot of a problem. There are 2 screenshots. You just check your WhatsApp group and read the problem which is there. And let's try to find out the solution of the given problem. For you, I'm reading the problem from the image. An electronic game contains 3 components arranged in the series parallel circuit shown in figure 12. At any given time, each component may or may not be operative, and the game will operate only if there is continuous circuit from P to Q. Let A be the event that the game will operate, B be the event that the game will operate though component X is not operative, C be the event that the game will operate though component Y is not operative. Using the notation in which 0001, for example, denote the component Z is operative but components X and Y are not. List the sample space and the elements of events ABC. Determine which of the events are mutually exclusive. First of all, let us try to do this particular part which is defined on the problem, and then we can calculate the probability as well. So I hope that you have seen the screenshot. I hope you have seen the screenshot. So I'm going to, I could have written the question, but this will just kill the time. So I have decided to send you the image of the question. I'm going to the next page. So a gaming circuit is there, which is defined in the following way. So this is the circuit, and they are saying that the circuit is game will operate only if there is continuity from the point P to point Q. The game works if there is continuity in the circuit. There is continuity in the circuit. They have defined several events. Capital A is the event representing that game will operate. So I'm writing it over here. Game will operate. B be the event that game will operate. Game will operate though component X is not working. And C is game will operate though component Y is not working. And a notation is there given, which is which they are calling it as 001. this implies, this sort of notation implies that X not working, Y not working, Z working. And they have asked you to define the sample space. They have asked you to define each of these individual events. Okay, so let's do it quickly. Sample space will contain how many outcomes? Sample space will contain 8 outcomes. Okay, so what are the outcomes? That none of these parts X, Y, and Z, they are working. They are not in working mode. Then we have this particular part that Z is only working. Then we have this particular part that Y is only working. Then we have this part, X is only working. Then we have this part, all of them are working. Then we have the following, X is working, Y is working, but Z is not working. Then we have the following, X is working, Z is working, but Y is not working. And then we have this, X is not working, but Z and Y are working. So how many events are there? 8 events are there. 2 cube, 8. If I try to write this is my sample space. This is my sample space. If we try to write the event A, that the game is operating through component X, though component X is not working, that means according to this, our event will be component X is not working, but the game is working. Now see, game can only work if there is a continuity in the circuit. Component X is not working. Component X is not working. So according to this, we can say that the game will work if we have this situation, that component X is not working, but Y is working and Z is working. There is a continuity in the circuit, so the game will operate. Okay, so just let me check. Okay, and C is the event. No, they are using the notation as follows. They are saying that this is my capital A, that the game will, okay, sorry, this is my sample space. This is my sample space, it is all right. This is not my event A, this event is my B. Game will operate though component X is not working. So only 0, 1, 1 will remain over there. C is the event that game will operate though Y is not working. So the only event is 1, 0, 1. And A is the event that the game will operate comes from 4 events. What are these? Game can operate only when there is a continuity in the circuit. Okay, so we have 1, 1, 1, we have 0, 1, 1, we have 1, 1, 0, we have 1, 0, 1. So there are 4 events: 1, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1. So you can see that chat box is now, I am enabling the chat box so that you can put your attendance. Okay. So you can see that this, all these events A, B, C, they are actually the sub events of capital S. Okay. Now, if I ask you the question that which of these events are mutually exclusive? Question is, which of these events are mutually exclusive? If I talk about AB, if I consider B and C, you will see that B and C, these events are not disjoint. Not disjoint. Sorry, these events are disjoint events. No common elements are there. If we talk about B and A, we will find that these events are not disjoint because 0, 1, 1 is the common element. 0, 1, 1 is the common element between these. So these are not disjoint. If I consider the event A and C, you will find that there is a common factor which is 1, 0, 1. So they are also not disjoint. What have not been asked in the problem is about the probability. They only wanted to know that whether you can understand how to construct the sample space or not. Okay, this is very important for us, for them, because once you construct the sample space, you immediately can calculate the probabilities. So you see that now quickly I can calculate all the probabilities of the event A, B, and C, because we have the entire knowledge of the sample space and its respective events. Now, probability of A that the game will operate will be what? Will be 4 out of 8, which is half. Probability that the game will not operate is 1 minus half, or you can count the respective events as you like to do always. Probability of B is what? Probability of B is 1 by 8, and probability of C is 1 by 8. Okay, because only one event is present. Only one event is present out of all the events. Only one event is present with respect to the sample space capital S. With respect to the sample space capital S, I'm saying this probability is 1 by 8 and this probability is 1 by 8. In the next phases of class, you will get to see that when we talk about the probabilities, the notion of the sample space or the mother set should be in, we should keep in mind, because if I change the sample space over here, then the probabilities will change accordingly. Here I can say, I'm not going into the details of this because that particular situation has not been discussed yet. This is another phase of our course curriculum, the next phase of our course curriculum. But here, remember that I have calculated the probabilities over here, keeping in mind that my mother sample space is capital S. With respect to that, I have assigned this value. I have not calculated, I have counted and assigned these values. So with this, I'm going to conclude my today's session. Thank you so much for being patient in this particular class. And I don't know whether I was able to convey the knowledge of probability in a different way to all of you or not. If anything which is not clear to you, you can always put your doubts. You can ask, I will give you the way, but the medium by which you can do so. And I'm actually stopping over here right now. The next class will be on next week. 2 single class will be taken from the college environment, and Friday's class will be taken from the home environment. Whenever I will take the class from the college environment, there may be some noise. So I'm in advance, I'm sorry for this sort of inconvenience. Okay. So thank you so much. I am going to stop my share and end the session. Good luck.